Okay, so today's lecture is about systems. So the first lecture was about signals, and since this is kind of like a discrete time signals and systems course, we need to talk about what are systems, okay? And so, like I mentioned on the first day of class, systems basically process signals to create other signals. That's the most simple way of thinking about what does a system do. And so, as we talked about before, you can imagine that there is, you've got some sort of pressure on your, gas pedal. That goes into some sort of complex control system that is your car, and what comes out is the velocity of the car. I mean, that's a super simplified version of things, but that's kind of like big picture, right? I got one signal that is driving the other signal, and it's processed through this system that decides what that other signal should look like. Or you could imagine, this is not just an electrical engineering concept, right? So you could also imagine something like, I've got the price of 1 barrel of oil on day N. That goes some goofy system, which is the economy, to be very simple. And what comes out is basically, the price of a gallon of gas. Right? So if you were thinking about it, you could imagine that, the price of the gallon of gas lags behind the price of a barrel of oil by several days while it gets refined and stuff like that, and then people add taxes and stuff like that. So there's some sort of weird system that the economy does to produce that number. So a lot of times we usually represent the action of a system on a signal to be something like this. I have x of n. It goes through this box, right? A lot of times you'll see the box represented like this capital H, and what comes out is another signal. Or sometimes if we're really all talking about the same thing, you could say something like this. Sometimes you see it said like this. These are all different ways of saying the same thing, okay? And so when we talk about a system, we're talking about this H. And we're going to learn in a few weeks why I use this capital H. So for those of you that have already, skipped ahead, we know that this is, sometimes we think about the H. This capital H would be like the frequency response of the system or the transfer function of the system. We're also going to talk about the impulse response of the system, in which case we might use a small h. We're going to talk about that in the next lecture, okay? And so, for example, we may specify the entries of y of n as functions of the entries of x of n, right? So for example, I might say something like this. Y of n is the sum from k equals minus 2 to 2, let's put a 1/5 out here, of x of n minus k, right? And if I write out what this means, it's like saying, okay, I've got 5 entries of the signal x that are getting added up and averaged to produce the entry of y, right? And this is actually a special case of what's called a moving average filter. And just as an example to see the action of how that works, so let me make a Matlab example here. So let's just take some random signal. Right, so here's some sort of noisy signal, right? So I can define my system as basically this, thing that's going to act on entries of x, and then I can make my y as filtering h by x. Did I mean this? I don't know. I thought there was a help filter. Am I wrong about this? Oh, maybe it's filter. This is why you practice before class. Filter BAX. Oh, I see. So I would say go away. And now if I make another plot of y, what I should see is that this is kind of a nominally smoother signal compared to the original, right? It's kind of like I'm taking away this spikiness, right? And if I were to continue to filter that signal, so say I filter it again, kind of double filter, and then I plot it, I can see that now things are getting even smoother, right? So that's why it's called the moving average. It's like saying, take my buddies around me and average out. And what that's going to do is it's going to mitigate the spikiness and turn things to be smooth. If I kept on filtering it forever and ever, I'd eventually get down to basically like a constant signal, right? Okay, and so switch back to my talking here. So another situation that you see a lot, and we're going to talk about this not right now, but later on in class. So in continuous time, you see a lot of systems that are described by differential equations, right? So you may see something that looks like this, right? So these kinds of systems come up in things like, you know, mechanical properties of masses and springs and stuff like that. You have forces and accelerations and things like that. And if you were to take the continuous world and discretize it into digital, you would end up with something that's more like what's called a difference equation. So you might see something that looks like this. And the reason that we make you take differential equations as an engineer is that you need to learn how to solve these systems in order to figure out if I give a certain input, what is the output, right? And so you had a whole semester of differential equations where you learned about how to do this kind of thing. As we'll see, the machinery of DSP makes solving these systems much easier, right? So I mean, when you took differential equations for the first time, you probably had a lot of this like, okay, let's guess what the thing might look like. We know that using things like Z-transforms, these things can be super easily solved, okay? So let's just say difference equations arise from I would say electrical and mechanical problems. Okay. So certainly life is not made up of just usually a single system, right? So a lot of times we have to connect systems together. And so I would say connecting systems. And this kind of has an analogy to circuit design. So you guys have all done circuit design. So you're kind of used to the idea that I may have a signal that goes through one system and that goes through another system, and then I get my final output, right? So I may make a bigger system out of a bunch of subcomponent systems, and that's really naturally the way the world works. Or I may have something, and this would be like serial connection. Serial, or sometimes you see this called cascade, right? And this may be kind of the way that your stereo works, right? So it goes through your, preamp, it goes through your graphic equalizer, it goes through your, something else, and then it comes out of your speakers, right? Or I could have something where I have a signal that goes through multiple systems, and I combine those multiple systems at the output to get my final signal. And again, that's a lot like, it's like your graphic equalizer, right? So you want to say, okay, I want to, pump up the high, or pump up the bass, decrease the midtones, pump up the high notes, and so this would be a parallel system, similar to what you did in circuits. And then you might have something that's more like this, where I have a signal that, I'm going to leave a little gap here, I guess I might as well put it here, where I have one system here, and then the output is fed back through here, and maybe I have, this kind of feedback system, right? And so this is kind of like the way that the cruise control in your car would work, right? You have an input, which is your pressure on the gas pedal. Then you also have to look at what is the corresponding output, and you feed the output back into the input to be able to figure out, okay, well, what effective system do I want to apply to the input in order to derive a certain control law, like the car goes at a constant speed. Okay. And so we're going to talk about different instances of these types of systems throughout the class. Okay, okay. So any questions so far? All right. So let's talk about some basic system properties. Okay. And so the easiest one is causality. And what this means is that a system is causal if the output at time n only depends on the input up to time n. Right? So for example, a system like this, where the output depends on the current value of the input and the value of the input 1 unit ago, this is causal, right? A system like this, where I'm looking at the value of the input 3 units from now, is not causal, okay? And so it's easy to check, is the system causal? Well, you just have to see, does some future time appear in the equation for the system, right? And so you might ask, well, okay, so I mean, is every real world system causal? Yes? Anyone against? No. All right, so it depends on the way you think about it, right? So there are certain systems, for example, your car is causal, right? Your car can't do anything that, it doesn't know how you're going to steer, how you're going to brake, a minute in the future, right? So some systems like these real-time systems, for sure, they have to be causal, right? But then it depends on how you think about your signal, right? So for example, think about my graphic equalizer, right? So when I design a filter for that, the graphic equalizer doesn't have to only be processing the time, from now previously, right? I mean, there's no reason why I can't read all that signal into memory and process it, in the future, right? So for example, certainly your graphic equalizer has some sort of buffering in it, right? So it's looking forward to make sure that it provides you with the music prior to the time that you actually hear it, right? Another good example of things that are not causal are things like image processing, right? So for example, if I have a one-dimensional signal, right? The idea is that I imagine these are my units of signal, right? And so here's perhaps the time that I'm at. Causal says that I'm only looking at this point and previous times, right? But, what if those signal samples came from, a boat that was stringing along with it a bunch of sensors, right? And these sensors are just collecting data, right? So here's a case where there is a sequence, there is a natural ordering of the sensors, but I get all the sensor input at the same time, right? So it's not like I can't process all this stuff at once. And the same is kind of true for images, right? So if I think about an image, if I want to blur an image, usually what I do is I take the pixel that I'm at and I average it with its neighbors, right? And if the system was strictly causal, I would only be allowed to think about the neighbors that were kind of strictly before I got to this pixel, right? So for example, a causal 2D system, I would only be allowed to think about stuff kind of up to this point, whereas this blurring kernel is using stuff that appears kind of later in the image, right? So it kind of depends on what your interpretation of the n is, right? It is true, I mean, it's kind of a trick question that, obviously no system can look into the real future, right? But, it all depends on how you construe the dependent variable n, okay? Okay, so causality is easy. The next property is linearity. And this is really important because we kind of are hoping that systems that we process are going to be kind of sensical, right? So there are kind of two properties that go up with linearity. One is that if I have the sum of two signals, when I put them into the system, what comes out is the sum of the two outputs, right? So let me just be a little bit more clear. So the hypothesis says that x1 goes into the system and produces y1, x2 goes into the system and produces y2, and the idea is that when I add those two signals together, put them through the system, I should get the sum of the corresponding outputs. This property is called additivity. The other property is that if I multiply one of the signals by a constant, that when I put it through the system, what I get is the correspondingly multiplied version of the output. And this property is called homogeneity. And you can kind of combine these two together when you're testing for linearity to, instead of testing for both of these things separately, you can just test that if I have, something times the first signal plus something times the second signal, I put it through the system, what comes out has to be the corresponding kind of weights on the outputs. And this has to be true for any input signals, right? So I can't just test it for, let me put the delta function in and see what I get, let me put the step function in and see what I get. If it works for those things, then I should be fine, right? You have to prove that this is true for any possible input signals to the system. And we're going to show how that proof works in just a second. So, the intuition is that the system is kind of acting proportionally on the input. And, that is true for a lot of real-world systems, right? So the intuition is, for example, if I pedal twice as hard, my bike should go twice as fast, right? If I put twice the effort in, if I push twice as hard on the refrigerator should go twice as far, right? Those things are, lots of real-world systems obey those kinds of things. But not all systems are linear either, for sure. So, for example, if I work on a test and you work on a test, and we get our separate scores, and then we work on the test together, and we get the score that we get with both of us working together, that's not linear, right? So maybe you got an 80, you got a 70. When you work together, it doesn't mean you get 150, right? So there are a lot of systems that are not really linear. And so we need to, either confine ourselves to talking about linear systems or find a way to find the closest linear system to the system that we actually have. And you'll find that, there's lots of work. We're not going to talk about so much in this class, but if you take a more advanced class, one of the things that you learn about is called linearization, which basically means how do I take what I've got and find the closest linear system to it. Okay, so how do we prove whether a system is linear or not? Well, that means that we need to kind of have this kind of symbolic pair of signals, and we test whether this new signal has the right output. So let's consider an example. So let's suppose that this is the system that I'm given. So if I have some arbitrary input signal x of n, what comes out is x1 of n minus 2, x1 of n minus 1. If I have some other arbitrary input signal, what comes out is this. We're going to call this y1 of n, and we're going to call this y2 of n. Okay, and then the question is, what is the response to some new signal that is the sum of these two guys? Well, so let me just say that when you're doing these kinds of linearity proofs, and also for the time invariance proofs we're going to talk about next, you can never go wrong by being really, super ploddingly methodical in your proof, right? Because it's a little bit tempting to skip through the steps and say, oh, I can tell this is linear, I can tell this is time invariant, but this is the right way to do it. So here is my new signal, right? When I put that new signal through the system, what I get is z of n minus 2 z of n minus 1. Now I substitute, what do I know about z of n? This is x1 of n plus x2 of n. This is minus 2 x1 of n minus 1 minus 2 x2 of n minus 1. And now I can recombine those things and say, hey, actually what I did get was the sum of the outputs, right? And I say, okay, this is, in fact, the sum of the outputs. And so now I have verified that this is correct. Okay. And the same way, I could say, okay, now instead, let me consider this guy. And now what I could do is put that into the system. So when I put Zn through the system, I get a Zn, which is equal to a x1n minus 2 x1 n minus 1. And I can see, yes, that is exactly what I got, right? And so, then I can say homogeneity is confirmed. Now, it's a little bit of a pain to have to do these two steps for every time I want to do this. And so let's do it all at once, right? So an easier way to do it all at once is to say, okay, let's suppose that we have two constants, right? So all at once. Let's say I have z is equal to a x1 of n plus b x2 of n. I put that through the system. What I get is z of n. I feel like I did something wrong on the previous page. I think I'm okay. Oh, I know I did wrong. No, this is what I did wrong. Sorry, forget I said that. So go back to this. What comes through the system is this, right? I get z of n minus 2 z of n minus 1. Then I plug in what I know. This is a x1 of n minus 2 a of x1 of n minus 1. And then I resort. This is the a times this, and this is a times y1, right? Sorry about that. I knew I did something wrong here. So let me do this right for this. So what I get is z of n minus 2z of n minus 1. And now I substitute, what do I know about z? Well, this is equal to ax1 of n plus bx2 of n minus 2 ax1 of n minus 1 plus bx2 of n minus 1. You can see where this is going. And now I can resort this stuff. And then I can see this is, in fact, the linear combination that I expected. And so when you do the homeworks and when you prove things are linear, it's usually easier to do it this way. It is true that some systems can have the additive property but not the homogeneous property, and vice versa. So it's not like one necessarily implies the other. In theory, you have to take both, or you have to do it this way. Okay. And so in terms of how would you guess whether a system is linear, well, usually the linear system is made up of basically, instances of the signal that pop out like previous signal values, okay? But, it takes a little bit of practice to be able to tell, okay, can I inspect this visually and tell whether it's, linear or not? So let's take a look at this signal. Okay. So, linear or not linear? Who votes for linear? Few people. Who votes for not linear? Few people. So, and 50 abstentions. Okay, so basically we have to check, right? So, I mean, instead of guessing, you have to figure it out. So, let's suppose that I have x1 goes into the system. What comes out is 3x1 n plus 5. I put x2 into the system. What comes out is this. Now let's suppose I put z, which is equal to, well, let's just put the sum of these things into the system, if I'm just going to check additivity. Well, I put that into the system. What I get is 3z of n plus 5. I plug in what I know about z, which is it's the sum of these two things, plus 5. And now I ask myself, is this equal here to this plus that? And the answer is no, right? Because if I added these two things together, I would get the 3 times the sum plus 10. Here I only have the plus 5, right? So, not linear. Okay? And so, if you're trying to show, or if you suspect that something is not linear, you can just prove it with a counterexample, right? You give me one signal or a pair of signals for which one of these properties fails, right? If it fails for one, that's all you have to do, right? And so the easiest way to prove that something is not linear usually involves simple functions like constants or delta functions, right? So in this case, let's suppose that, a counterexample. Let's suppose that my x1 of n is just equal to 1 for all time. And let's suppose that x2 of n is equal to 2 for all time. Okay? That means that if I put in 1 into the system, what I get is 3 times 1 plus 5 is 8. If I put in 2 into the system, I get 3 times 2 is 6 plus 5 is 11, right? And so here I could immediately conclude the system is not linear, right? Because since 2 is twice 1, this should be twice 8, and it's not. So if the system was linear, I'd expect 16, instead I got 11, right? And so this is all you have to say, or I guess maybe the way to say it is like this. This is all you have to say to tell me the system is not linear, okay? So when you're not sure, try some very simple functions, right? Don't try anything too crazy. Constants, delta functions, those are the best, okay? Okay. So, questions or comments about linearity? So, another useful property, just as a side note, is that since I'm an expert, I could tell this immediately wasn't linear. One thing that has to be true for a linear system is that, remember that homogeneity is part of the linearity statement, right? So homogeneity says that if I multiply this by something, what I have to get out is the same multiple of the output, right? And since this has to be true for any constant, I could choose 0, right? So if I put 0 in here, that means that a linear system must have, if 0 goes in, that if a equals 0, 0 has to come out, right? And we can see that wasn't true for this system over here, right? Put 0 in, I got 5 out. So that's immediately a tip-off. Question? Does A need to be real? I think that for our purposes, we're always going to be talking about real coefficients. I think that if you're talking about general linearity, then A could be any number you want, any complex number, right? And in fact, the realness of the coefficient will never come into play when you're doing your proofs. So it doesn't really matter. Other comments or questions? Okay. So another property that's really important is called time invariance. Okay? And so this means that the system behaves the same way regardless of when I apply the input. Okay? So that's the kind of intuition, is that system behaves the same way, regardless of when input is applied. And so mathematically what that means is that if I put a signal into the system and I compare it to what I get if I delay the signal by some number of units, what I should get out is the same output delayed by some number of units, right? And so, again, the intuition is that many real-world systems should be time invariant, right? So if I decide to bake some toast at 3 p.m., I put the toaster in, the toast comes out at 3:05 p.m. It shouldn't be any different if I go and put my toast in at midnight and it comes out at 12:05, right? So the time that I do something shouldn't depend, shouldn't affect the system, right? But again, you can think of many systems that are not time invariant, right? So for example, think about the speed it takes you to download something at 3 p.m. versus the speed it takes you at midnight, right? So clearly internet traffic is highly, non-time invariant, right? And so there are lots of, and again, just in the same way that we try to find the closest linear system, sometimes we try and, wangle a system into being time invariant, but sometimes it's a lot harder, right? Because, lots of real-world systems are not time invariant. So we have to make a model for what the system is doing as a function of time. Okay. And so again, we have to prove or disprove this is true for a given system. And so this, I always find that people have a little bit more of a hard time with. So I want to do a couple of careful examples to show how that works. Okay. So again, let's take our same system that we had before. So this is the system from before. We have x of n minus 2 x of n minus 1. The question is it time invariant? So what we need to do is, again, we make a dummy signal. So let me call my signal z. And this time, the dummy signal is going to be a shifted version of the input. Okay. And now, I guess I should have done this all on one page, but let me see if I can do this a little better here. So now what happens if I put z into the system? Well, what comes out is z of n minus 2 z of n minus 1. Okay. And now I plug in, what do I know for z? I know that z is equal to x of n minus n0. And here, again, I plug in what is z of n minus 1. Just to be really pedantic, I'm going to say you always just kind of follow. I plug in n minus 1 into here and n minus 1 into here. So I get n minus 1 minus n0. And then I ask myself, is this equal to the output shifted by n0? And what would that be? Well, that would be, again, if I follow this up here, it's like saying I plug in n minus n0 into here. So I have that equals x of n minus n0 minus 2x of n minus n0 minus 1. And I can say that, hey, since this subtraction order doesn't matter, I can compare these two things and say, yes, I got the correctly shifted output that I was expecting. Okay. And so a common mistake is to always seem to come up with the fact that every system is time invariant, right? So let me show you an example of a system that's not time invariant and how you would, kind of come up against it. So what about this system? Okay. So same kind of deal. What I'm going to do is I'm going to say let z equal a shifted version of the input. Okay. Now, when z of n goes into the system, what comes out is z of n squared. Right? because when x goes into the system, what comes out is x of n squared. So now I figure what is this? So z of n squared, I have to plug in n squared whenever I see an n here. So I get x of n squared minus n0. And now I ask myself, is this equal to the shifted version of the output? And for that, I have to plug in this wherever I see the n here. And so what I get here is x of n minus n0 squared, which is not the same as what I came up with when I put z through the system, right? So this is a non-time invariant system. So until you try and do this yourself, I think that it's kind of hard to see the difference. But after you work a couple examples, you can see the virtue of this approach, right? If you do it this way, you will never get a time invariant question wrong, where you just kind of plod through, okay, I need to make this separate signal, see what happens to that signal, substitute in what I know, and compare it to the shifted output, right? Part of the issue is that, you know, you're comparing two signals, right? You're comparing the shifted version of the output to what happens to the response of the system to the shifted input. And until you verify that those two things are the same, you can't assume anything about the system, right? You don't know exactly what the system may be doing to the signal, okay? Again, in the same way that all you need to do to prove that something is not linear is to find a counterexample, the same thing is true for time invariance. You may need to use a different signal to be able to get at the counterexample, but still, things like delta functions are generally a good way to start. So, counterexamples to time invariance, try delta functions. So let's take our system again, right? So what we had here was y of n is x of n squared, okay? And so let's think about what happens when we put the delta function into the system, right? So what is the response to this function here, delta function, which, just as a reminder from last time, is something that is 1 in the middle and 0 everywhere else, okay? Well, what should we get? That's like saying that, if I just kind of plug in, that's like saying that y of 0 is x of 0, y of 1 and y of negative 1 are both equal to x of 1, y of 2 and y of negative 2 are both equal to x of 2, and so on. And I can see pretty fast that if I put the delta function in, that y of 0 is x of 0, that's going to be this. All the other values are, again, going to be 0. Right? So this is the response of the system to the delta function. Now, what is the response to the shifted version of the delta function, right? So let's suppose that I have a delta function that is shifted by 1 unit to the left. Okay. Well, that would be a signal that would look like this. And again, what would I get if I put that through the system? Well, I would apply the same system rule. I would say, okay, well, y0 was whatever x0 was. y1 and y minus 1 are both whatever this number is. So I'm going to get zeros here. So I'm only looking at positive values of the signal, right? Since there are no positive values of this shifted signal, I get 0 across the board, right? And in this case, I would say, I shifted the output left by 1 unit. The output did not shift left by 1 unit like I expected it would, right? So again, this would be sufficient to prove that things were not time invariant. Okay. And so just again, to be kind of clear on terminology, right? So we're going to talk, I may get to it a little bit today, but we're going to talk about next time a lot this concept of impulse response, right? Which means that when I put the delta function in the system, I see what I get out, right? Now, technically, I can only really talk about the impulse response, or the impulse response is only really a useful quantity if the system is linear and time invariant, right? So here's an example where, yes, I can compute the response of the system to an impulse, but knowing this so-called impulse response doesn't mean the same thing as we usually do when we talk about LTI systems, because I can't talk about how the system responds to any other signal in terms of the impulse response, right? I can't get to this output knowing that this is the response to the impulse, right? So be careful talking about the impulse response until you're sure that the system is linear and time invariant to begin with. Okay, so I guess I kind of skipped forward, but let me just ask a question. So questions about time invariance. Okay, so again, if you took signals, you probably proved these kinds of things with continuous time systems, and so the same idea applies to discrete time systems. And so on the homework, I ask you to prove or disprove linearity and time invariance for a certain system or two, and you have to figure out how it works. Okay, and so kind of putting it all together, the thing that we care about the most in this class is linear time invariant systems. And these are often called LTI systems. Okay? And so from now on, or at least for the, until I tell you so, we're going to assume that the systems that we care about are all linear and time invariant. Okay? The reason for that is that it allows us to analyze how the system works in an extremely elegant and powerful way, right? Which corresponds to the impulse response, the frequency response, the Z-transform, all that kind of stuff is not possible if the system is not linear and time invariant. Okay? And so let's just say that real-world systems are often modeled as LTI. And the reason is that, let's just say often a good approximation. There are lots of, systems that are almost linear and that linearity is kind of good enough. Analysis is very easy, powerful. Right, those are the main reasons. And so you would take a whole, and that's not to say that you can't analyze non-LTI systems, right? So for example, if you go further up our course curriculum into the 4,000 and 6,000 level, there are courses on, you'll see a course called nonlinear control. What that means is how do you design control systems for nonlinear systems, right? So it's not like you have to just throw everything away if you don't have a linear system. But, when you guys are first starting out, we're not going to get too deeply into nonlinear systems. And so the key idea is that LTI systems kind of tie together all the stuff we talked about so far. This idea of delta function, differential equations, superposition, all this stuff comes together in this nice way. So the key concept is what's called superposition. Okay, and what do I mean by that? Well, kind of what I mean is that, just to kind of preview how this works. So if I were to take a combination of, let's say I take some signal, x, and I represent it, I take a bunch of shifted versions of that signal. I guess if I was smart, I would have labeled these like this, so the numbers match up. Plus ... If I put that into an LTI system, pen is dying. Well, what should come out of that LTI system is corresponding sums of signals like this. Right? that's like saying that, well, from the linearity part, it's like saying that I can take apart each of these sums and coefficients separately, right? So I know that I can kind of go from here to here, from here to here, from here to here. Time invariance tells me that the shifted version of this x is going to be the shifted version of this y. It's not like this possibly could produce some other weird, output signal, right? So basically, I'm writing the output of this LTI system entirely in terms of knowing what happens to just the original signal, okay? And so this is really important because what we care the most about is the delta function, okay? So, consider an arbitrary signal where we have, whatever these values look like here. And I want to know, what does this signal come out as after I put it through an LTI system, right? And so what I can think of is this signal is like, and let me just write, some numbers here that tell me how tall each of these sticks is. So I can think about this as saying, well, this looks like this simple signal here plus this simple signal here, where everything else is 0, plus this simple signal here, and so on. Dot, 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 right? And I can furthermore kind of decompose this by saying, well, that looks like, this very simple signal here multiplied by A0 plus this same very simple signal shifted over multiplied by whatever A1 is, plus this same guy shifted over times A2, and so on, right? Which is like saying I have A0 times the delta function plus A1 times the delta function delayed by 1 unit plus A2 times the delta function delayed by 2 units. That's a crappy delta. And so on, right? So what I've done is I've taken my original signal x and I've taken it apart into pieces that involve the delta function, right? And to say this in a more mathematical way, sorry, I guess I cut off the right-hand side of it. To say this more mathematically, that's like saying that my x of n is the sum of the values of x multiplied by corresponding shifted versions of the delta function. Okay. Now again, that looks kind of scary, maybe, but if you think about it, this delta function, right, is only, this delta function fires basically at n equals k. And when it fires, what is this value? It's whatever that x of k is, right? And so again, we actually already introduced this in the last lecture, right? This is sometimes called the sifting property of delta functions. Right? Because kind of one way I think about this is that here I have infinitely many functions added together, but basically only one of these functions is not 0, right? Because if I plug in, n here, that's like saying, well, the only place where this delta, as a function of k, the only place where this thing is not 0 is when k equals n, right? And when k equals n, I get x of n, so this is kind of like almost like a syllogism. Okay. So why is this exciting? Well, it's exciting because it means that we can ask ourselves, what happens when we put this signal through the system, right? So first of all, let's suppose we have an LPI system. Right? And now I'm assuming that. That's very important, right? So I put the impulse function in. And let's call the output of that h of n, right? So this is the unit impulse, also known as the delta function. Right? I put that into the system, and we're going to call what comes out the impulse response. Okay? And we always use little h of n as the response to the delta function. Okay? So now the super exciting thing is that I can figure out what is the response of the system to any input x by looking at only knowing what the system did to the impulse. Okay? And so let's plug this into here using my properties of linearity and time invariance. So, what is the response to xn? Well, I'm going to say my response of the system to xn is going to be writing it like this large sum. And now I can say, okay, well, from the purposes of this discussion, right, k is just, xk's are just numbers, right? They're just numbers that are multiplying the heights of the delta functions, right? So they're going to play the role of constants for the purposes of understanding how the system is processing these sum of delta functions. And so from linearity says that I can immediately take these constants out of the sum and also, look at the sum of the responses like this. I can basically immediately say that my output is like these constants times whatever the system does to this set of signals. And by time invariance, I can say, well, that response of the system to the shifted delta function is going to be the shifted version of the impulse response, right? So if k was equal to 0, I would just have the regular impulse response. If k was equal to 1, it would be like the impulse response delayed by 1, right? And so this is really exciting, right? Because this tells us if I only knew the impulse response of the system and I tell you some new signal, this is how I combine those two things to get to the output of the system, right? And so, as you may know, we call this the convolution between the input, so the output is the convolution of the input and the impulse response. Right? So that's really exciting, right? It means that the LTI system can be entirely characterized by what it does to the delta function, right? I don't need to keep some crazy table of this is the input, this is the output, this is the input, this is the output. I don't have to record all that. All I have to know is the impulse response, and then for any input signal that I get, I can make it, come together into the correct output, right? And so this is really the thing that all of our analysis hinges on, is that the impulse response fully characterizes the system. So the impulse response fully characterizes the system. Sorry. Okay, so questions about that key idea. So, as you may recall from a previous class, this convolution process is kind of tricky, okay? And so I think what I want to do is save convolution to next time and talk about the mechanics of doing convolutions for both finite length signals and infinite length signals. We'll talk about that a little bit more next time. But I think this is a good place to stop. So we stopped a little bit early. That's all right. No one has a problem with that. And so any questions or comments? Okay. All right, so before you shuffle around, first let me just stop my recording.